So first thing, we have released you a grading of product 3. You should be able to check it out. A pleasant surprise to me is a lot of you did really well, actually. So I'm really happy for that. And you should feel proud of yourself too for being able to do well on product 3. I think more than half the class got 100 points, which is really good performance. I really appreciate that. Okay, your effort and the passion you put into your code. I think if you score 100 or anything above 90, you should feel really proud of yourself, because this is definitely not an easy project. I've been very honest with you from the beginning that this is a challenging project. So well done. Okay. And project 4 was due about 25 minutes ago. I just shut off the submission site. Most of you should have submitted your code already. And I'm not going to release project 5 today. I will release project 5 on Thursday when the homework 4 is due. So I will release project 5 on Thursday, which is to implement sort, merge, join. So project 5 is about. And we are not implementing the refinement version of this. Meaning we're not doing this. So this is not what we're doing. What we're doing is and this is essentially that. So we move down. What? So this is this one. Okay? So if you think about this logic, this is down. Right? That's your project 4. And I will give you a .o file for the sorting. In case you didn't finish your project 4, you have a bug in your code. So you can use my .o distribution instead if you're not confident in your own code. But you can just use your code from project 4 to do this. So all you have to do for project 5 is essentially this, which cannot be simpler, if you ask me. Like 2 loops, check, move, then you're done. So project 5 is really a giveaway, right? I think, to help you smooth into the final period. Okay. All right. So that's project 5. And homework 4 is due on Thursday, and I will give you a few days to review it. I think we will lose the Thursday. Are we still going to have a lecture on Thursday next week? Is it part of the Thanksgiving holiday or it is before?
That's Thanksgiving.
That's in Thanksgiving. So that's unfortunate for us. I definitely hate losing a class. So what I'm going to do then is to do a quiz on Tuesday. Okay, so because I will release the solution to homework 4 on Thursday, which you can review on Thursday, Friday, Saturday, Sunday, and Monday. So that we will do that quiz on Tuesday for whatever covered in homework 4. And then, of course, I will finish discussing cross minor today. On Tuesday, we start talking about transaction. Then that's your Thanksgiving holiday. You do your project 5, and when we come back from Thanksgiving holiday, I will use another 4 lectures, I think, to finish the discussion on transaction, concurrency control, and crash recovery. And in the midst of that, I will release the last homework. And once we finish that, we immediately do a quiz, and then we spend 1 or 2 lectures on NoSQL and things like that, then we wrap up the class for the final test.
Yeah. How much time will we have for project 5?
You can have until, I'm thinking 1 week after Thanksgiving when it is due. So I will give you plenty of time. If you need more time, let me know, because we have no more project after this. So I do have some leeway. I can cut some slack if you guys feel that's needed. Okay? Question?
Did we use Canvas that ironing was not working?
Ironing was not working. But this morning we checked, we got most, if not all, submissions.
I think the online.
The online, the web interface might run into the same problem as what happened in project 1. So that's something controlled by Kate, nothing we can do. But the command line submission I checked always work. Never had a problem.
There's no way to actually going back my file and see if it has.
For that, we can check the top to the TA and go and verify. And if there's a glitch over there, we will definitely allow you to resubmit without any penalty. Okay? Yeah.
And when is the final exam on 18th?
Good question. So the final exam is slated at December 18th. Keep in mind, I have no control over that. That's according to the university schedule. They schedule the final using some scheduling system they run, right? But some of you send request to me a month or 2 months earlier, said that for various reasons you need to leave early for the Christmas holiday. For example, you get married, things happen, stuff like that. Okay, so if it's a valid reason, if it's a really sound excuse, I will honor that. What I can do is I can do test ahead of time. There is a slight chance we may be able to do the test during the last lecture. So that's what I'm hoping we can do. But given the progress we're making, that's more than likely that's not going to happen. So we have to do it on December 18th. And of course, that I need to get a pull from you guys as well. Whether you want to do an early test or you want to do December 18th. Some of you may prefer do it early, finish, and get rid of it. Some of you may think, I need a little bit more time to prepare, so it's better to do December 18th. So I will get opinion from you guys, but it looks like we will do on December 18th. And for those of you, I think only 2 or 3 of you requested that. If you have absolutely valid reason to leave early, let me know, and I can arrange an early test for you on the condition that you are not going to leak the problem from the final test to anyone else.
But December 18th is Friday and we have class on Thursday. So will it be on 17th December?
Well, 17th, that's the final week, so we no longer have lectures. That's the same. And I don't think we can do December 17th because the university schedule things around and we cannot get hold of this lecture anymore, lecture hall anymore by that time, by December 18th, on December 17th.
Is the final cumulative or just for everything after the midterm?
Final will be exactly the same format as midterm, meaning open book, subject to the same policy, and it will test only the materials after the midterm. And it will be based on your homework 4 and homework 5, and quiz 4, quiz 5, of course. So those are the scope of your final test. So if you know how you prepared for the midterm, you just do the same drill and prepare for the final, you should be okay.
Start from extendable hashing, the content.
Start from the dynamic insertion deletion of B plus tree, because the dynamic insertion and deletion of B plus tree was not tested in the midterm. So everything after that, including the dynamic insertion deletion of B plus tree, will be subject. Will be the scope subject of the final test. Okay. All right. I think that's enough of the main stuff. Let's go on to the lecture. So I think from last lecture and the lecture before that, so this is where we stopped. I think by now I should have convinced you, I hope I have convinced you that SQL queries can be dramatically optimized depending on the query plan you use. And there will be a huge difference in performance if you are not careful in selecting which plan to execute the same query, right? The same query. So the only thing left is for us to understand what's going on inside the database engine, inside the database kernel. How does a database kernel actually optimize a query, right? Given an input SQL query, how does the kernel take the input plan and transform the plan into various forms and select one that has arguably the best performance among all possible plans? And this is unfortunately not an easy task. And people, of course, you need some formalization and some formal argument, but people have shown that this QR optimization problem is actually NP-hard. In other words, if you want to find the best QR plan, unless P equal to NP, it's unlikely we are able to do that in polynomial time. I mean, it's not certain. It's not like you definitely cannot, because we don't know whether P equal to NP or not. But it's unlikely we can find polynomial time to find the best plan. So in practice, given that knowledge, in practice, what most database engines do is to get rid of bad plans. Get rid of bad plans. And so that you are left with some okay plans or some good plans. I don't know, of course, which one is the best, but I can just, even if I randomly choose one from the remaining ones, I'm not going to be, I'm not gonna lose too much in my performance. Okay, so this is still is much better than having no QR optimizer and choose the bad plan, because we can see the performance between the worst plan and the good plan, not necessarily even the best plan, but the difference, the gap between the worst plan and good plans can be huge, right? So using the running example I showed you last lecture, we started off from more than 500,000 IOs, and we drive down all the way to less than a few thousand IOs. Okay, so there's a huge difference. So what does the QR optimizer rely on to perform its optimization? Well, it uses these modules to carry out its optimization. The first thing is that it relies on the iterator interface from a database engine. The iterator interface, we talked about it earlier. Every single operator, which actually you're going to implement in project 5, the sort word join is presented to you as the iterator interface. So it has a close, has an open, initialize, next, essentially. And that's what you're going to implement in this project. That gives you a feeling what this iterator interface looks like, right? So it relies on this iterator interface so that it can interact with different operators very easily. Because all operators, no matter what your semantic is, it has a common iterator interface that the QR optimizer can call. Okay, so that's point number one. Point number two, it needs a cost estimation. A cost estimation gives you a rough estimation for the cost of a given QR plan. So the input is one QR plan, output is an estimation for the cost in terms of I/O, or in terms of a cost that's a weighted sum between I/O and CPU cost. Okay, I talked about this briefly last time, right? You can build a cost model to establish relationship between I/O cost and CPU cost. Of course, in modern architecture, this cost model becomes more and more complicated because multi-core and multi-threading, all that stuff, right? But still, an important observation is we're not going for the best plan. We're trying to find an okay, good plan. So some approximation, some error in this cost model we can afford. Okay, so that's the key observation. And in cost of estimation, we really need two things. One is selectivity estimation, meaning given an input query, I need to estimate how selective this query is, meaning what percentage of records this query will be able to retrieve for me. And that's important. I argued this for you last time, right? If you do a range query search, and if you know you have B+3, typically, no-brainer, you go with B+3. But if you know your selectivity is very low, by the way, selectivity low meaning that you are selecting a lot of records. Selectivity high means that you are selecting very few records. If you have very low selectivity, in the extreme case, for argument's sake, let's say my selectivity is 0, meaning that you are effectively selecting all records from the database, then having a B+3 or not is irrelevant. You just do linear scan. So using that extreme case argument, you can see the importance of the size estimation. And now, after we have understood the different join operators, you should be able to appreciate this size estimation even more. Why? Because, for example, take hash join as an example. How do I know the cost of your hash join is 3 times n plus m or not? Well, you need to know n and m. You need to know the size of the input relations. If the input relation is a base table from the database, then the size, the value of n and m are trivial, right? It's given essentially. You just measure this, how much space it occupies on disk. But what if this relation R and S, or one of them, is an intermediate result produced by a joint of another two relations? Then this value of n and m is no longer available to you. And how do you know whether you should use hash joint or some other joint algorithm for joining this intermediate relation with another relation? That could be a base relation or yet another intermediate relation. You follow me? So the size estimation is critical, right? Because that tells you which algorithm you can apply and what is the corresponding cost. And size estimation and reduction factor, meaning selectivity estimation, actually go hand in hand, as you can tell, right? So these two have a strong correlation between the two, right? If you know how to do selectivity estimation, chances are you can do a very good job in estimating the size of the output, especially for single table operators. For single table operators, that's always the case. If I tell you the selectivity, you can immediately derive the size of output. For multi-table operations, meaning join over multiple tables, this is not so obvious, right? Even if I tell you the selection predicate, the selectivity for each selection predicate on each table, the join might still change the size dramatically. Give an example. Okay, I have magnitude, I have only one. And I ask you what's the size of R joint S. Well, the point is, this could be, the value of this could change dramatically depending on the value distribution in S. Right? For example, in case 1, I may have all 3, then the size is 0. However, in case 2, even though I only have a single value of 1, I may have a million of ones here that still blow up the size of the output. You see my point? So even if you have selection condition 1, selection condition 2 are R and S, and I tell you the selectivity of this, it still doesn't really help you much in estimating the size of the joint. For example, I may have million ones, and I tell you my selectivity is 10%. Can you tell me the joint size? Well, you cannot, because it really depends on whether that one is selected or not. And this is a harder problem than estimating selectivity, because selectivity is to estimate the size. But now you are asking me to estimate the distribution of the selection. These two are different. If you have a solution for the latter, meaning you can estimate the distribution of the output, you have a solution for the first. You can estimate the size. But if you have a solution for the first, you do not have a solution for the latter. You follow me?
Could you use the selectivity to give like an upper bound?
Yes, totally. You can use selectivity to give an upper bound. The upper bound, of course, the worst case is the size of the intermediate results from the two joints, the cross product of that. But this, unfortunately, in many cases, is not a tight upper bound. In fact, if you have n tables, if you have, let's say I have k tables. Size n each. What is the upper bound of my joint over these k tables? You would think is n to the power k, right? Of course, I have to phrase my question properly, a tight upper bound. Meaning that in the worst case, you can actually find a joint that gives you n to the power k number of output. Because otherwise this is meaningless. Of course, okay, I can give you an upper bound like this. What's the point? But how much money Feifei has? Okay, $1 billion. useless, right? Yes, it is upper bound, but how useful is that? Okay, I take back what I said. I don't want to limit my potential earning, right? So maybe I can make more than $1 million. Who knows, right? But you see my point, right? So interestingly enough, okay, this is actually quite surprising. When I first saw this result, it's not obvious actually. The type upper bound for this problem is actually not n to the power k. It's actually less than, much less than n to the power k. That's actually quite interesting. So I'm not going to go into details, but that's something you can think about. And another related problem, since we're here, is what is the optimal quote-unquote what is the optimal joint algorithm? Well, if I have a joint like that, okay, one obvious argument you have is, in the best case, the cost of your algorithm has to be at least equal to the size of your joint, because you have to print them out. You cannot possibly skip looking at even one of those. You have to look at all of, in order to find exact joint results, you have to look at least one of them, each one of them at least once, right? So if I use J to denote the size of this, I can argue any joint, the cost of this will be greater or equal than J. I mean, this is assuming the best case, right? Note that J might be much, much less than this, and even less than a single table size n, right? This is assuming that you are kind of like, you do this magic, somehow from this joint tuple, you look at only the joints. Right? You don't look at any other one. You don't waste your time looking at any other one. And this is kind of like magic, right? But there's something called a worst case optimal joint algorithm. And actually, this is fairly new result. Last year and this year, there's a paper, you can Google this, called Leapfrog. It's a very funny name, Leapfrog joint algorithm. So it works like a frog, and it leaps around. That's why it's called Leapfrog. And this algorithm, people prove that this is the worst case optimal joint algorithm. Meaning that in the worst case, its cost, okay, and in most cases, its cost will be just this, just equal to the joint size, which is actually a little bit surprising. So read this. Now come back to quantifier. So we need this cost translation. We also need some, data summaries and statistics about your tables. Like, you have seen from the running example I gave you, right? How many pages in the setter, how many pages in the reserve, what's the page size, how many tuples in a page, how many records you have, and how many attributes you have, what's the size of each attribute. Things like that. That's what we call data summaries or statistics. These are basic ones. You have more complicated ones, more advanced ones like histogram and kernel density estimate, like the discussion I gave you, I think either last lecture or the lecture before. And these information are stored in a place called catalog, right? The catalog stores the metadata information about your database, including those data summaries for your data and the schema information for all your tables. That's what kind of data the catalog has. And we also need this, relational algebra equivalence. You may wonder why I need this. Well, you do need this in order to generate equivalent query plans. Given an input query plan, you want to be able to transform this query plan to multiple different query plans while working with one constraint, which is you cannot change the semantics of query, right? You cannot say, oh, I changed the query plan from this to this, and this gives me much better performance, but instead of selecting CS and math student, now I'm only selecting the CS student. Well, guess what? That's really cool, but it doesn't work, right? You change what you want. And then, once you have all of this, choosing alternative plan, that's kind of become obvious, right? So you use relational algebra equivalence to generate many different equivalent plans, and for each plan, using the stats and the catalog information and the cost estimation, you get a rough estimation for the cost of that plan. And you do this in a loop. You keep doing this until you have to be careful because there are so many possible equivalent plans. You don't want to spend all your time in just iterating through all possible plans because remember, this step itself takes overhead, introduces overhead. And to a point, the overhead of doing this, if the overhead of doing this is more expensive than executing the query itself, then there's no point of doing this anymore, right? So typically what databases do is set a threshold on either the number of plans you tested or a threshold on upper bound of the time you are willing to spend on this. So you go until you meet that threshold, then you stop and you keep the best plan you have identified so far. And you say, I'm going to live with that. It's kind of like searching for a house. You can keep looking on the market, but at some point you have to put a stop and go with the one house that you like the most from the houses you have seen so far. You can always argue, if I wait a little bit longer, there will be nicer, better house available on the market, but you have to balance off. Right? So that's what this does. And this last point is less obvious, and I don't want to discuss this in this class. But the point is, in a database system, you do not have a single user system. You have a multi-user system, meaning that the database system is going to handle multiple queries at the same time. And this is both a challenge and an opportunity, if you think about it. It is a challenge because you have to schedule resources carefully so that you can serve each query with minimum latency possible. It's an opportunity in the sense that maybe different queries will ask for similar queries. So instead of executing them one by one sequentially, having them all coming in together at the same time give you the opportunity to optimize across multiple queries. And I'll give you a simple example to illustrate my point. So this is one of my work on multi-core optimization. Of course, we optimize this for, we did this for Sparkle. Sparkle is a query language like SQL, but for graph database. Okay, for graph database. So you can skip all the details. I show you one figure, and you can tell, you can see the point of this multi-query optimization. Okay, suppose these are your input queries, right? So I represent this query as a graph. Because it's a graph database, so I have to represent my query plan as a graph rather than as a tree in relational case. In relational case, we represent my query plan as a tree, but in graph database, I have to represent my query plan as a graph. Right? So this is a query pattern, I should say, not necessarily even query plan, not query plan, just the query pattern. So what this is asking for, the query one asks for this pattern from the underlying graph database. So it's a subgraph matching problem. Right? So you find the component from your graph that match this subgraph right there. And so you have 4 queries over there. So if you execute this query one by one, you have to execute query 1, query 2, query 3, and query 4. But if all 4 queries coming in at the same time, you can make this critical observation is that the 4 queries are very similar. In fact, they share a common component, which is this component right here. So what I can do is I can extract out this common component and execute this part only once. So I will get a set of subgraphs that match this. And then, in parallel, I check the additional constraint for query 1, query 2, or query 3, query 4, and push the results to query 1, 2, 3, 4 respectively. And this is going to be better than executing query 1, query 2, query 3, query 4 sequentially, because in that case, this will be especially useful if this part is highly selective. You follow me? And in relational database, you can leverage on pretty much the same observation. Right? For example, give you a simple example. I may ask for a CS student with GPA between 3 and 4. And another professor at the same time may ask for CS students with GPA between 3.3 and 3.6. What observation can you make? Well, don't execute the second one. Execute the first one, and then just take the subset from the first one and give it to the second one. You are better off than executing both of them sequentially, one after another. Okay. So that's margin core optimization, which we will skip. Okay. We will skip from this class. So we focus on these issues, and we will use what we call system R style optimizers. And what is system R? So system R stands for relation, by the way, relational. System R was a system designed and implemented by IBM Research back in early 80s and late 70s. And it was the first prototype of a relational database engine. Of course, this guy from Oracle, the story was that he learned about System R, and he basically, let's use the word "use" idea, and built this thing called Oracle, right? And System R, of course, nowadays is gone, right? It's just a research project people remember and say good things about it, but that's about it. But Oracle, no matter whether you say good things or bad things about it, it generates billions and billions of dollars, right? So there's a difference between research and taking research into the next level, right? I think that's what Oracle has done. Okay, but we will focus on System R optimizer, and it's a very simplified optimizer if you compare that against today's commercial database optimizer. However, most, if not all, commercial database optimizers are based off this System R style optimizer. So if you understand this, you will have no trouble in understanding other optimizers inside the commercial database engine. So the first thing, the first observation is that in System R, the unit of optimization is actually not an entire SQL query. The unit of optimization is actually a block from your SQL query. This actually explains, and this actually, to my knowledge, is still the case for most, if not all, commercial database engines. This explains why, in many cases, if you write a nested block query in a database, it typically will take a long time to execute. You know the reason why? The reason is they optimize the block separately, even if you have strong correlation between the blocks. Do you remember the query example I gave you when we talk about nested queries? I mean, you can think about as a nested loop, right? And the inner loop has some sort of dependency on the outer loop, on the current iteration from the outer loop. And if it's in a compiler, if you think about a compiler, actually, loop optimization is a big deal in compiler. And this kind of interdependency and correlation between inner and outer loop is actually a great opportunity for compiler to optimize. If you have taken a compiler class, you know what I'm saying. However, in database optimizer, yes, I argue that there is a strong connection between nested query and nested loop, but they're not essentially the same. There's still some subtle difference. So people cannot just borrow those optimization technique from compiler into optimizing a nested block with correlations. So the simple approach is to simply treat them separately, but the downside of that is you might lose very important optimization opportunities. Okay. I think I can give you a concrete example of this. if we go back to the lecture on SQL, about which one we talk about nested blocks? Is it the first one or second one? Look at this example. So this is the nested block. All you're doing is this. Actually, you can write this query. You can write this query using a join. Right? You can write this query using a join between singular and reserved. And in fact, writing the query using a join will give you a much more efficient plan. Because what you're gonna do, what the database engine gonna do is realize that's a natural join between singular and reserved. And more importantly, it's a foreign key and primary key join. Why that matters, by the way. Why foreign key, primary key join is good in terms of efficiency. Someone tell me?
Primary key, we have the cluster index on that.
Yes, that's one reason. Typically, you will have a cluster index on the primary key. But let's say even that's not the case. We don't have a cluster index. Primary key and foreign key join is still very good.
It's the equation.
Huh?
It's the equation.
It's an equal join, and why that's good?
Your selectivity is going to be extremely high.
Excellent. If you think about it, the key observation is actually related to the join size. What is your join size in this case? If it's a primary key, foreign key join, and if you draw them out as a graph, if I view my join as a graph, can I? Okay. So I draw each tuple as a node. So I draw this as a bipartite graph. What can you claim about primary key, foreign key join? Well, it's always going to be a 1 to many many instead of many to many many. And that's good news. That limits the join size dramatically. So you're only going to have things like that. You're never going to have things like this because there's a key constraint. And database engine can do this type of join really, really fast because it boils down to using just the hash join essentially. And in linear calls, you can do this. Whereas, if you think about this, if you implement this using a nested loop, right? What's going to happen? Well, in the worst case, you end up with quadratic calls. So you are talking about linear cost versus quadratic cost. And the sad story is the query optimizer, typical query optimizer cannot do nothing about this because it optimizes the block separately. So they will never be able to figure out, oh, I can rewrite this query into a join and that give me equivalent output.
The graph here, you would just have one edge from the right side going to the, or excuse me, one edge from the left side going to the right side, but you have multiple edges going into the node on the right side.
So you got like
two edges coming out of each.
Okay, let's try to draw. You have one edge coming off from R to S.
Right.
Let's say this, okay?
And then you could have like the next one down on the left side.
Oh, you mean you'll have another relation here?
No. So
Okay.
the next node down on the left side under
Okay.
R. Under R.
And R, okay.
And go into the top one like that. But you couldn't have two edges coming out of like that one that you're pointing at, right?
Well, by the way, if this is your primary key, and if this is your foreign key, this kind of
I see you switch. Okay, never mind.
this is impossible, right?
I was switched around. Okay.
So since I draw this graph, let me just comment a little bit. Join and graph, we recently found in our research that join and graph actually has a strong connection because of this. So if you extend this to multiple tables, well, if I just draw this graph to the next level, you see what I mean. So suppose that's my graph. And what can you claim about join? Well, join, the results, the join results is nothing else but what? But a complete path from one end to the other end. And that's actually the intuition language in leapfrog, but they didn't phrase this as a graph problem. But once you realize that, you know how joinable these relations are, quote unquote. I make up a word, right? How many joins they're gonna have. Essentially has a strong connection to how connected they are in this graph from one end to the other end. In other words, how many paths exist for me to go from Salt Lake City to Boston. And that's somehow connected to how joinable between Salt Lake City and Boston. No matter how many intermediate relations you have in between. Okay? So one way to do join is to simply do what? Do random walks. You perform random walk on this graph. If you start doing random walk, if you can somehow reach the other end, that gives you a join. If you get stuck, like you random walk, you come here, you stuck. That means that doesn't give you a join. So the success probability of the random walks give you a what? Let me ask somebody. A very important thing we just talked about. Give you a success estimation for the join. The success probability of your random walk give you a success estimation for join. And success estimation for join is an extremely hard problem, as I will talk about in a minute. So this actually give you a good estimator for that. Yeah.
I still can't see why, like, couldn't you in the extreme case have into the case?
Have into the power k case.
Yeah.
So we take that offline. It is not obvious. Yeah.
The quantitative is the max flow problem.
Max flow. Well,
That's not a totally-
but yeah, we are looking for total connected paths. So I have to think about it. Let's talk about this offline. I have to think about it.
Right, you just got an extra node on the left and an extra node on the right, and you connect everything, yeah, like that, and you do it on the other side, and you do your max flow.
Yes, but in that case, finding the one important concept I didn't mention is, in order for you to do the random walks, a key observation is you don't actually have to materialize this graph. Because by the time you materialize this graph, you have already done the join. Then estimating the size makes no sense. But the point is, doing this random walk, you don't need these lines. How many of you play Age of Empire? I played that game, right? It's by Microsoft. And Age of Empire, at the beginning of building your base, what do? You send out this what we call farmers. And they die, you don't care, right? And your map is dark. You send the farmers out. And what do? They wander around. They explore, they wander around. You see a tree blocked, you turn around, you go this way. So the good thing about random walk is that you don't need to materialize this graph. You start from here, randomly select node. At this point, you see the edges only on this node. And you randomly choose one, go to the next level. Think about this as the farmer in Asian Empire. So the point is, performing random walk is much cheaper than computing the full join, because you don't really need to see the graph in order to do the random walks. So that gives you a good way to estimating the size of the join. Yeah?
So you figure out the edges. For figuring out the edges, you need to scan the entire.
So in order to identify these edges, actually, that's a key argument, right? In order to find, how do you find these edges? Don't you have to do a linear scan of these guys in order to find these edges? A key assumption is that you have index here. you have index available. And that's why, again, primary key, foreign key join is convenient because typically you have index on keys. So these are available anyway. So using index to identify this guy costs you almost no time.
So how do you wrap what should you do?
Oh, that's something. Okay, I'm writing a paper so you can read it in a few months. All right. So, all right, let's come back here. And I will show you, by we finish this, I will show you we actually implement this in PostgreSQL. And performance improvement is huge. I can show you what we got later on. But let's come back to QOptimizer. Okay, so that's assumption number one. It's not ideal, but we have to live with something. Most optimizers make this assumption. So they optimize Unix separately, ignoring the correlation that potentially exists between different blocks. That's observation number one. Observation number two. For join, they consider this thing called left deep join trace. Left deep join trace. Why people do this? By the way, this is a left deep join tree, meaning that at each node in this tree structure, your right-hand side is always a base relation. Your left-hand side can be a base relation or an intermediate join result. And that gives you a left deep join tree. For example, this is not going to be, and this is not. Okay? Because you have a node whose right-hand side is not a base relation, it's an intermediate result. That violates the definition of left deep join tree. And you may wonder why people consider only left deep join tree. Shouldn't you consider all these possible plans? Well, we have to limit the search space. Because if you consider all possible plans for join, you can easily show that that has exponential growth towards the number of relations you have. And forget about cost estimation and all of that. Simply enumerating through this plan space will be exponential in time already. And no QOptimizer can afford to do that. So I have to limit to something that has a reasonable size. So people go with left deep join trace. Okay? So those are two assumptions you want to keep in mind. I'm going to use the same schema for example. Okay? Same schema as examples. Reserve and receivers. The first step in QOptimizer is what we call the parser. The parser will take SQL as input and translate that into relational algebra. And we didn't do a parser project in this class, right? But this is very similar to your typical parser in any programming language. In fact, it's actually simpler than your parser for language like C++ and things like that. Why? Because SQL is declarative, meaning that the parser only needs to remember a few keywords and do a rule-based parser. You know what I'm saying, right? See this keyword equal to this, see this, do that. So it's a rule-based parser. So it's fairly straightforward, simple to do this. If you can do C++ parser, then you definitely can do SQL parser. Okay? So there's nothing much I want to say about here. So that's a translation from this to here. You simply translate SQL to relational algebra. And you use the system reserve keyword to do this transformation. Select equal to sigma. Oh, sorry, select equal to pi. I still make this mistake. Select actually is projection, not selection in relational algebra. So select is pi, and so on and so forth. So that's step number one. Step number two. Now you have an input curve plan, right? So you have an input curve plan. That's a direct translation of your SQL from the parser. So from the parser, you get a direct translation of your input plan. But this plan might be really bad. And you want to find an alternative good plan. To do this, we use something called plan equivalence or relational algebra equivalence, really, because your plan is represented by relational algebra. So you use relational algebra equivalence to test whether any two given plans are equivalent. Once you are able to do this, you can do transformation and morph operations to convert one plan to many other possible equivalent plans. So let's talk about relational equivalence. For most of them, it's actually trivial. For example, isn't this trivial? Right? The selection of n conditions is when you use the CNF. What is CNF? Conjunctive normal form. When you express your condition as CNF, and we talk about this for any Boolean expression, first order logic, you can always convert that into an equivalent CNF form, conjunctive normal form. Okay? First order logic, you can always convert that to CNF. And once you have a CNF, you have this equivalence, which is what we call cascade, which is executing the CNF is equivalent to executing the condition one by one after another. And they also satisfy this rule of commute, meaning that the selection, which selection condition you execute first doesn't really matter. So that's for selection. For projection, it's a little bit trickier. If you do a projection on attribute 1, you can convert this to an equivalent plan of projecting out many other attributes. Condition on each of this contain A1 as a subset. Each of this contains A1, the final projection, as a subset. Then you can do this. For example, project out Caesar name is equivalent to project out Caesar name and Caesar ID. But it's not equivalent to project out only the Caesar ID. And for joins, it satisfies both association and this rule of commute, meaning that you can combine any two joins together and do the remaining join after. This combination is arbitrary. You can do this or this. It doesn't change the end results. Yes.
So do you just try random permutations of these, or is there like a structured plan for final?
Yes. However, that random permutation is big. The size of that random permutation is big. For n relations, the random permutation order is n factorial, and you cannot afford to do that.
So you only consider left?
So that's why you only consider left if three.
So you don't consider all permutations?
No, you don't. You cannot. You cannot afford to do that. And you can also change the order they are in the join. We actually leverage this fact already. I mean, if you think about block nested join, we argue you can always use a smaller relation as order. But the fact you can do that is because of this. Because which one is the order doesn't change the join output. There are more equivalents. And like I said, a lot of these equivalents are obvious, right? Like a projection commutes with a selection that only use attributes returned by the projection. Right? So you can selection first then projection is equivalent to projection first then selection if the projection keeps all the attributes used by the selection predicate. Selection between attributes of the two arguments of a cross product converts a cross product to a join. Right? So that's essentially what we said. A selection on just attribute of R commutes with R join S. And this is the famous rule of pushing down operators. We leverage this in our running example, right? Essentially, the fact that you can push down selection operator is because of this. It's because of this. That's why you can push down the operator. Most operator you can actually push down, right? But some of the newer ones that people do cannot be pushed down. I talked about this before. For example, if I have a sample operator, this means sample row percent from R. Let's say I want to produce a 1% sample of my table. Okay? This operator unfortunately cannot be pushed down. Why? The reason is in fact, even if you push down on one side, it still doesn't work. That's not pushing down on both sides. Similarly, if a projection follows the join, you can push down the projection subject to the condition that not only you keep the projection attribute, but also the join attribute. Then you can push down the projection. Now let's talk about cost estimation. For each plan considered, we must estimate the cost. And the cost dimension depends on two things, essentially. Nothing else but two things. One is input relation size. You need to know that. Input relation size. And the algorithm you use to implement the operator in concern. For example, if it's R join S, all you need to know is the size of R, size of S, and which algorithm you use for the join, whether it's a block nested join, or hash join, or merge sort join. If you know this information, you can estimate the cost. Do you agree with me, Mark?
Wouldn't you also want to know like selectivity?
Well, if R and S are base relations, no, you don't. You know the size of R and S. And well, for cost estimation, you don't need the selectivity estimation. Why? Because for cost estimation, we do not count the output as part of the cost.
Or the selectivity would only be for deciding like.
Selectivity will be useful, will be needed if this is not your final output. But this, R join S, will be used by another operator down in the pipeline. In that case, you will need to estimate the size of this, because for that operator down the pipeline, I need to know the size of this. That's essentially your selective estimation. But if you just want to estimate the cost of R join S, it actually doesn't depend on the join size.
So we're not looking at the whole tree. We're just looking at one.
Looking at one operator. Yes.
Okay.
Yes. But immediately, yes. See in tree, right? You must estimate the size of the result for each operator in the tree. Now, if you talk about the whole tree, then what Charlie just mentioned is needed, right? Because now you're not looking at just one node in the tree, but you are looking at the tree as a whole. You need to know the intermediate size in order to estimate the cost of the next operator down in the pipeline. And the cost, as I said, for the most part we focus on I/O, but in most optimizers nowadays, they use a sophisticated cost model to capture both the I/O cost and the CPU cost. And they even go, as far as factoring in, the effect of multi-threading and things like that. However, for this class, let's just keep it simple and try to understand the basics. Let's say our cost model is simply to count the IOs. Okay, how about that? Okay, so we will keep that in mind. And the statistics and catalog. What are some typical information over there? Well, you need this kind of things: number of tuples, number of pages, distinct key values. You may wonder why I need to know distinct key values. This will be clear in a minute. It's useful for joins, actually. you need to know the distinct values in order to do, in order to estimate the size of the joint. I'll give you a simple example. I come to that later on. So anyway, we're gonna talk about joints. Right? And you need to know low key and high key. Why you need this? Because typically, on a given attribute, if I do not have a histogram for the distribution of that attribute, for the values of that attribute, I will simply assume a uniform distribution. And to be able to use the uniform distribution, what do you need? You need to know the range of your values. That's why you need to know the low key and high key. And this is a very simple, lightweight summary you keep. So most databases just keep this for free, almost for every single attribute. Because I simply assume uniform distribution. And for attributes of great interest, I will go all the way to build a histogram to get a better understanding of its distribution. But for most attributes, I simply assume they're uniformly distributed. Make sense? And you may wonder, why not we build a histogram for each one of them? First of all, histogram as the one I talked about last time, you use the dynamic programming to build it, right? Meaning that it's quadratic cost in building it, right? Dynamic programming. And so building a histogram is expensive upfront. And in case of updates, maintaining a histogram is another challenge. Think about, actually that's an interesting problem for you to think about. Once I gave you this optimal histogram construction, I minimize the variance within each bucket. How do you handle updates down the road? Can you maintain this histogram incrementally? Rather than rebuilding this from scratch every time. So last year in Srikumar, this year in Srikumar, 2015, there's this dude from MIT. He's an undergrad student. He's a first year PhD student. But the time he wrote the paper, he was an undergrad student. For the first time, he designed an algorithm, which is an approximation, that gives you this histogram in linear time, not quadratic, and be able to do incremental updates in almost constant time. And the approximation is a constant approximation too. So that's really cool, right? You can go and read that paper. Where I am. So for each index, I need to know the height of the index and the number of pages in the index, right? The size of the index. And the size of the index matters, by the way. I argued this for you before, but let me just argue this again. You cannot build, you cannot just build any weird index as you want, because size of the index is a big concern if you want to build an index in the database, right? For example, in the extreme case, let me give you an argument. I can pre-compute the answers for all possible queries, and then build a hash index on this. My hash key is your query, essentially. My hash entry is answer for that query. And you argue now I have this most efficient database engine nobody can beat, because any query my query time is constant. The query come in and hash the query to its answer. How can you beat me? How can you possibly beat my solution? But the size of this index, this hash index, is humongous, right? Think about it. I mean, the possible queries you can have. If you have one-dimension range query, just one-dimension range query, and we talk about discrete domains of n values, even just for that, what's the size of this index? It's n squared, because you can have n squared possible range queries. You follow me? So typically, a requirement for indexing database system is to be at most linear in size. Sometimes we can afford a size of n log n, for example, but definitely not beyond that. And catalog, when do you update this information? Well, in most database engines, they update this periodically, meaning that they update this at like midnight, every night, when the load in the database is at a minimum. They do not maintain this information live in real time, because the cost of maintaining that is simply too expensive. Of course, there are database engines that try to do this for some of the important attributes live in real time. Okay, because why? Because maybe those are the attributes of those are the information my course might rely on most often. So I want to make sure I have a good estimation for that up to date. So some database engine will try to do this in real time, and the challenge there though is to figure out what attributes or what statistics you want to maintain real update for. And this may change over time. For example, in September time or August, maybe the registration table is the one that you want to maintain live updates, live information about, not on the students table. Because during September or August time, that's when people actually rely on the registration information the most. But then back in October, once you go into October, November, do you still need to maintain live updates on registration? No. I expect almost no change if you talk about data summary sense from one night to another night on registration, because there are very low activity going on. So the challenge is how can you figure out these kind of things automatically? And then there's a word for this called database auto-tuning. And there's a project started by Microsoft Research back in early 2000. They did just that. And this now has been merged into SQL Server. Since I believe since SQL Server 2005, they have incorporated this called auto-tuning. The stuff we talk about, things like that, traditionally are the responsibility for the database administrators. And that's why database administrator makes a lot of money, because over time you accumulate that experience, and those experiences are specific to this particular database, this company's database, because it depends on how you set up the database, what's the structure, what kind of index you have. So over time, the database administrator becomes indispensable for that company. Because you can find another good database administrator, but he or she may not know the structure of your database as well as the current one. So you kind of you're being hijacked by this database administrator, right? Because the database becomes so complicated, and your workload has been so much optimized for that particular database, and you don't want to just replace your administrator and hope the next guy can just come in and do as good job as the first one. Okay? But auto-tuning kind of mitigate that problem a little bit by taking away some of those responsibilities away from the administrator, database administrator, and hacks that into the database kernel. Okay. More detailed information such as histogram are sometimes stored, but not always. As I mentioned, this because this is expensive to maintain. Okay. Now let's talk about size estimation and reduction factor. Okay. And reduction factor is essentially what we call selectivity. So I don't have to define this again for you. Okay. So here are some common size estimations. Some of them are trivial, but a few of them are actually a little bit tricky to understand. Okay. First of all, the result cardinality. This talk about multi-table operations. The max upper bound for cross product is this. The cross product upper bound is this. And this actually has a little bit to do with Charlie's question earlier. Why the upper bound for joint is not this? Because even if you have just one joint division, somehow we can prove that already make the query not the same as the cross product, even with just one joint division. It's impossible for you to make that to be still equivalent to a cross product. So the size of the joint must be smaller than this.
Even if they have the same of ones on both sides, because then you have to join every possible right?
We can talk about this offline. Okay. All right. So what about this term when you have the column equals value, meaning What's the selectivity of this? Well, the selectivity of this is this 1 over the number of keys you have on that. Suppose you have an index on that column. Suppose you have an index on that column. Why that's the case? Can someone argue this for me? Why is 1 over n key? By the way, this means the distinct number of keys, right? Distinct number of keys. Why? Why I use 1 divided by distinct number of keys? That gives me the selectivity estimation for this.
You just assume it's a uniform distribution.
You assume uniform distribution, so each key has roughly the same number of records. So selectivity, selecting one value is essentially 1 over the number of distinct keys. That's why earlier I said it's important to keep distinct number of keys in your catalog for this purpose. Of course, if you have a histogram on this attribute, you don't use this. You use your histogram because histogram will tell you a much better story as the frequency of this value. You follow me? But when you have no histogram, you, like I said, the default is assume uniform distribution, so use 1 over distinct number of keys to estimate. What about this? This is a little bit tricky actually. Again, we assume uniform distribution on both columns. So, what is this? What is this? What's the selectivity of this? Well, the formula tells you the answer is right there. It's 1 over the max of the distinct number of keys from the first and the second column. But why 1 over the max? Why not 1 over the mean? Why not 1 over the average? Do you see my argument? Assuming, of course, uniform distribution on both columns. Why that's the case?
As a step towards that, is it partially because the selection operation can be pushed into the join? So you can, doing the selection on the entire join is the same as doing the selection on each and then doing the join. Maybe that doesn't make sense.
It actually does. Essentially, you convert this to multiple selections. So this is equivalent to, let's say this is the, okay. You follow me? Or, right? Where these values are here. Do you follow me? Yes or no? Huh? Yes, right? Yes. I convert this as a union of column equal to value, which we have just discussed. Okay? And I know the selectivity for each of this. Do I? Which is essentially, all of this, they are the same, right? All of this equal to 1 over number of keys of A. All of this is 1 over number of keys of B. Because I assume uniform distribution on these values. So all of them are equivalent to this. Okay? You follow me? You follow me? And the final argument, which I will ask you to think about this a little bit carefully offline, is that this actually gives you overestimation. So we take the smaller value of the two estimates. That's why we take the max of the keys, which is essentially the mean of this, essentially equivalent to the max of that. Because these are overestimates. Both of them are overestimates, so I take the minimum of that. What about this? Well, this is equal to this. Why? Because you assume uniform distribution is become a range estimation. That's trivial. Okay? What about no index and no number of keys? All of these are not available. 10%. Why 10%? Don't ask me. It's just 10%. What about join? Join is tricky, right? Join is harder. Okay? Given a join of R and S, what is the range of possible result size? Actually, this is exactly the discussion we had just now, right? Exactly the discussion we had. For two tables, Charlie, you are right. It's R is n squared. Unfortunately, that doesn't carry out to k tables, to n to the power k, and that's something we can discuss offline. But let's talk about a special case. What if I have a primary key foreign key join? If I have primary key foreign key join, what is the size of my output? Can someone tell me that? R join S, natural join, right?
The size of the table you have the primary key.
What's the size of this? One is a primary key foreign key join. Suppose R is your primary key table, and this is your foreign key table. What is the size of the output? Charlie said it's equal to the size of R, which is not y.
The number of distinct keys on R times some selectivity factor of S, or some just times S, I guess, size of S.
Is essentially for every foreign key value here. Okay, one thing I tell you is we have integrity constraint in place. In particular, we have this key constraint in place, or what we call RI. Do you still remember RI? Referential integrity constraint. So RIC. Referential integrity constraint. Meaning that you cannot have a tuple in S having a foreign key value that does not exist in R. So this means, okay? It takes some thinking, right? But given this, you have this. Okay? It may not be obvious to you, but if you understand what I'm talking about, you still remember this, and this should be clear to you. Okay? Now, what about let me finish, and I answer your question offline, because I want to finish this. What about the general case? When I have a join on A, and A is not a key for either of the relation, because key join is simple. The estimation for key join is simple. I just showed you, right? What about non-key join attribute? What about non-key join attribute? We argue that it is this. Again, we assume uniform distribution on the join attribute. So this is very inaccurate estimation in practice. Very inaccurate, but still better than nothing. The point is, I can do this in two ways. I can go from R to S, I can go from S to R. When I go from R to S, what is my join size? Well, for each tuple in R, I expect to join with 1 over number of keys in S. This is for each tuple in R. And I have total how many tuples? So I get this estimation in the end. You follow me? Of course, I have to be clear on the joint attribute. A is my joint attribute. And that's my selectivity. If you talk about size, I need to multiply this with what? This is selectivity, by the way. If you talk about size, I need to multiply this with the number of tuples in S. This is your selectivity for one record in R. This is the selectivity for one record in R with the joint attribute on A. If you talk about size, you need to go over all the records in R, and then for each record R times the size of S. Okay, I have no space to write that, but this. So essentially, it gives you this. Do you follow me? For each tuple in R with the joint attribute on A, my selectivity is 1 over the distinct number of values of A in S. Okay? And when I iterate through all the records in R, I get that. And so the size for one record of R is number of records in S divided by this. When I go over all the records in R, I get this. And then you go around and do this direction, which gives you this. And now you have two estimates for the same thing. What do? You take the lower value of the two. Why? For the same reason I talked about earlier, when you do column 1 equal to column 2, those estimates are overestimates. So you take the lower one there, and you take the lower one for joint as well. This, again, assuming uniform distribution. For general joint conditions, and by the way, this only works for 2 tables. What about multi-table joint size estimation? And that's a much harder problem, which I will not discuss in this class. And if I have time, I can talk about a little bit about the research results we have currently ongoing. I can show you a lab demo Actually, multi-table joint size estimation boils down to this. Boils down to estimate the count of this. You follow me? So it boils down to estimate aggregation value, where the aggregation is count. And this can be generalized to multi-tables. And essentially, you want to build an estimator for this. Okay. All right, we stop right here. And next time, we're going to talk about enumeration alternative plans and finish off the discussion on augment.